morning, everyone. Thank you for joining us today. Welcome back to the Deep Dive. We've been looking at how computer systems fit together, especially with our last deep dive on system integration and diagnostics. But today, we're shifting focus. We're going beyond the desktop into the world of mobile and embedded architectures. Think about, the hardware in your phone, your smartwatch, even the hidden computers in your car or smart speaker. That's what we're unpacking. And helping us navigate this is our expert, bringing deep insights from computer science, AI, and networking. Welcome.
Hello, everyone. Thank you for having me. It's a great pleasure to be here to discuss this important topic.
Great. So our mission, as always, is to pull out the really key takeaways from our sources. We want to help you get up to speed quickly on the hardware and the thinking behind this mobile and embedded revolution. We've got a set of questions lined up to guide us, starting right at the heart of it with the system on a chip and going all the way out to the Internet of Things. So let's jump right in with a really neat analogy from our source material. How does this city versus arcology idea explain the fundamental difference between a traditional desktop motherboard and a system on a chip, or SOFI?
Yeah, that's a fantastic starting point because it really paints a clear picture.
Yeah.
Think of your typical desktop PC motherboard. It's like a city, right? You've got all these separate components, these different districts. The CPU is your downtown business district. RAM is maybe the residential zone. The GPU is the entertainment complex. I/O controllers are like the industrial parks.
Okay, I can see that. Separate buildings, separate functions.
Exactly. And they're all connected by, highways and roads. Those are the buses and traces on the motherboard. Now, this city layout, it allows for specialization, for upgrades. You can build a bigger entertainment district, swap in a new graphics card. But the downside is it's sprawling. It takes up physical space.
Mm-hmm.
And moving data between all those separate districts over those long connections, that takes quite a bit of energy.
Right, like traffic congestion and fuel costs in a real city.
Precisely. Now contrast that with the system on a chip, the SOS. The analogy calls it an arcology. Think of a single, massive, self-contained building. Inside this one structure, you have everything, the CPU, the GPU, the memory controller, I/O, maybe even specialized AI bits, all integrated as different floors or wings.
All under one roof?
Exactly. And the connections aren't highways anymore. They're like internal elevators and corridors. Super short, super efficient on-chip interconnects. So it's not just making things smaller, it's a totally different way of building the system. It's moving from separate parts you assemble to one highly integrated purpose-built unit on a single piece of silicon.
That arcology image really drives it home. It makes clear why this shift is so huge. It's not just incremental improvement, it's a different philosophy. So building on that, what are the specific concrete advantages that come from this tight integration? Why is it so crucial for mobile and embedded stuff?
Well, there are four really big ones that basically enabled the mobile world we know. First, the obvious one, reduced physical size. Putting everything on one chip drastically cuts down the footprint. That's how you get thin smartphones, tiny smartwatches. It just wouldn't be possible otherwise.
Makes sense. Can't have a pocket-sized device with a desktop-sized motherboard.
Exactly. Second, and maybe even more critical for anything running on a battery, is lower power consumption. It really comes down to physics. Shorter wires mean less energy to send signals. On an ET, you're talking nanometers. On a motherboard, it's centimeters. That's a huge difference.
Orders of magnitude difference.
Right. And that massive reduction in travel distance for data cuts, power used dramatically. That's the secret sauce behind your phone lasting all day, hopefully.
Okay, smaller size, less power. What else?
Third, you actually get higher performance for a given power budget. Because everything's so close together, communication between components is much faster, lower latency. The memory controller can be tuned perfectly for the CPU and GPU right next to it. This leads to a really balanced, efficient system that gets more work done per watt.
So it's not just about saving power, it's about being smarter with the power you do use.
Precisely. And fourth, there's lower manufacturing cost, but only at scale. Designing one of these complex SOCs costs a fortune upfront, huge R&D investment. But once you have that design, stamping out millions of identical all-in-one chips is cheaper than making lots of separate chips and then assembling them all onto a board.
Economies of scale kicking in.
You got it. That's a big reason why powerful mobile devices have become so widespread and relatively affordable.
Okay, that all makes perfect sense. Size, power, performance per watt, cost at scale. It's a compelling package.
Yeah.
But like you said, different philosophies have different trade-offs. What's the main drawback here? What do we lose with the SOCs model?
The big one, the one you as a user definitely feel, is the lack of upgradability. It's pretty much zero. because all those core components, CPU, GPU, memory controller, everything, are physically etched into that single silicon dot. They're permanent.
So no swapping out the processor for a faster one later?
Nope, can't upgrade the graphics,
Yeah.
can't add more integrated RAM, usually. If you want something better, you have to replace the entire SoC. And in something like a smartphone or tablet, that means replacing the whole device. Your phone's useful lifespan is basically tied to that chip inside it.
Right. So for you listening, that's a key difference from a desktop PC you might build or upgrade yourself. Your phone's more like a sealed appliance in that sense. Okay, let's shift gears slightly. Let's talk about the language these chips speak, the ARM architecture. We've mentioned it before. What's the key difference between ARM and the x86-64 we find in most desktops and laptops?
Yeah, this is fundamental. It's about the instruction set philosophy. x86-64, used by Intel and AMD, is what we call CISC, Complex Instruction Set Computer. Think of it as having a huge vocabulary of commands, some simple, some very complex, and they can be different lengths. To understand all these, the processor needs complicated, power-hungry decoder circuits.
Like a very sophisticated machine tool that can do many complex operations with a single instruction.
Good analogy. Now, ARM is RISC, Reduced Instruction Set Computer. It uses a much smaller set of simple, highly optimized instructions, and crucially, they're all the same fixed length. This makes the decoder circuitry inside the processor much simpler, smaller, and way more power efficient.
Ah, simplicity in hardware.
Exactly. The RISC philosophy basically says keep the hardware simple and fast. Let the compiler do the heavy lifting of breaking down complex tasks into these simple instructions. And that relentless focus on power efficiency is why ARM absolutely dominates anything battery powered. It's built for that world.
That CISC versus RISC distinction is crystal clear now. It totally explains ARM's success in mobile. But you mentioned it's not just the tech. Their business model is also key.
Oh, absolutely. ARM's business model is, well, quite unique and a huge part of its success story. ARM Holdings itself doesn't make or sell chips.
They don't. That's surprising.
No, they design the processor architecture, the blueprints, essentially.
Yeah.
And then they operate on an IP licensing model, intellectual property. Companies like Apple, Qualcomm, Samsung, MediaTek, tons of others, they pay ARM a fee to license these designs.
So they're selling the plans, not the finished product.
Exactly. And crucially, the licensees can then take that core ARM design and customize it. They can add their own custom graphics, their own AI accelerators, their own image processors. They build their own unique SoCs based on ARM's foundation.
That sounds like it would encourage a lot of competition and innovation.
It absolutely does. It created this massive, vibrant ecosystem where everyone is building on a common standard, but differentiating with their own additions. It's a big reason ARM became the de facto standard so quickly.
That's fascinating, a business model driving technological spread. And ARM keeps innovating on the core designs, too, like with this big little e thing. What's that about? Sounds like some kind of engine tuning.
Yeah, that's a decent way to think about it. Big. Little e is a really clever approach to balancing performance and power saving. It's what we call a heterogeneous computing architecture. What that means is, on the same sauce, you have two types of CPU cores, a cluster of high-performance big cores and another cluster of high-efficiency little cores.
Okay, fast ones and efficient ones, side by side.
Right. And the operating system scheduler is smart enough to know the difference. When you do something demanding, like launching a big app or playing a game, it throws the task onto the big, fast cores. But when you're doing background stuff, like checking email, playing music with the screen off, just idling, it shifts those tasks over to the ultra-low-power little cores.
So it dynamically switches gears based on the workload.
Precisely. You get the power when you need it, but it sips battery the rest of the time. It's a huge factor in extending battery life on modern phones while still giving you that snappy performance when required. It's hardware designed around how people actually use these things.
That really is smart design, adapting to usage patterns. Okay, so we've got the CPU with big little e. When we look inside a top-tier mobile cell, say an Apple Bionic or a high-end Snapdragon, what other specialized processing blocks are typically crammed in there? It's way more than just CPU and GPU now, right?
Oh, definitely. Modern flagship SoCs are incredibly dense with specialized units. Besides the CPU, multi-core, often big little RAM, and a powerful multi-core GPU for graphics, you'll almost certainly find an NPU, a neural processing unit. This is hardware specifically designed to accelerate AI and machine learning tasks right on the device.
Not for facial recognition or computational photography.
Exactly. Things like understanding your voice commands, making portrait mode photos look good, translating languages on the fly. The NPU handles that efficiently without hammering the main CPU or needing the cloud. Then there's the ISP, the image signal processor. This thing is crucial for cameras. It takes the raw data from the sensor and does a huge amount of processing, noise reduction, color correction, HDR merging, all in real time to give you that final photo or video.
So a dedicated chip just for making pictures look good.
A very complex one, yes. And finally, you have integrated modems. These handle all the connectivity, your 5G, your LTE, Wi-Fi, Bluetooth. They're built right into the SoC for seamless communication.
Wow. CPU, GPU, MPU, ISP, modems, all on one tiny chip. That arcology analogy just keeps getting stronger. What about memory and storage? Are they specialized for mobile too?
Absolutely. Everything is optimized for low power and high speed within that mobile context. For RAM, mobile devices use LPDDR low-power double data rate memory. It's a special version of the DRAM you find in desktops, but heavily optimized to SIP power while still providing high bandwidth. Standards like LPDDR5 push this even further.
Low power is the name of the game again.
Always. Yeah. And for storage, it's all non-volatile flash memory. In better phones, you'll see standards like UFS, Universal Flash Storage, or even NVMe-based storage, similar to fast SSDs in computers. These offer really high read and write speeds, which is why apps launch quickly and the phone feels responsive. Again, fast, but designed with mobile power constraints in mind.
Speed and efficiency. Speed and efficiency. It's the mantra. Okay, but beyond the desktop isn't just phones and tablets. There's this whole other universe of embedded systems. What exactly is a microcontroller, an MCU, and how is it different from these powerful objects?
All right, this takes us into that often invisible world. An embedded system is basically a computer system hidden inside a larger device to perform a specific function. Your car's engine control unit, your microwave, a smart thermostat, medical devices, they all have embedded systems.
They're everywhere, doing specific jobs.
Exactly. And the brain in most of these isn't a complex SoC like in your phone. It's usually a much simpler device called a microcontroller, or MCU. An MCU is also a computer on a chip, but it's scaled way down. It has a simple low-power processor core, a tiny bit of RAM and storage, like flash ROM, right on the chip, and importantly, lots of built-in input-output peripherals, timers, serial ports, analog-to-digital converters, stuff like that.
So much simpler, less powerful, but with lots of built-in connections for controlling things.
You've got it. It's designed for dedicated, often real-time controlled tasks, sipping minimal power. Compare that to an SoC, which is built for high-performance, general-purpose computing, like running apps and complex graphics. Different tools for different jobs.
That makes sense. And for a long time, programming these MCUs was pretty specialized, wasn't it? How did platforms like Arduino and Raspberry Pi change the game for embedded development?
Oh, they completely democratized it. It used to be quite a high barrier to entry, expensive tools, complex data sheets. But then came the open-source hardware and software movement. Arduino was a massive catalyst. It provided simple, affordable microcontroller boards with an easy-to-use programming environment based on C++ CIDI. Suddenly, students, artists, hobbyists, the whole maker community could start building electronic projects without needing an engineering degree.
It really lowered the barrier to entry.
Hugely. Arduino became the standard for learning, prototyping, and just tinkering. It made embedded accessible.
And then Raspberry Pi came along. But there's a key difference between, say, a regular Raspberry Pi 5 and the Raspberry Pi Pico, right? They aren't the same thing.
That's a really important distinction, yes. A standard Raspberry Pi, like the Pi 4 or Pi 5, is a single-board computer, an SBC. It runs a full operating system, usually Linux, on a relatively powerful ARM SoC. It's essentially a tiny, cheap desktop computer. You use it when your project needs an OS, networking, maybe a display more complex tasks.
Okay, so it's like a mini PC. What about the Pico then?
The Raspberry Pi Pico is completely different. It's a microcontroller board, like an Arduino. It doesn't run Linux. It runs your code directly on the hardware, what we call bare metal. It's designed for low-level electronic control, real-time tasks, interfacing directly with sensors and actuators, and it's very low power. It competes with Arduino in that space, not with the bigger Raspberry Pi SBCs.
Got it. SBC versus MCU board. A crucial difference for anyone starting a project. Now, many of these embedded systems, these MCUs, are being connected together to form the Internet of Things, or IoT. Thinking about these IoT devices, often out in the wild, what's the absolute #1 hardware consideration?
Without a doubt, for the vast majority of IoT devices, it's extreme power efficiency, even more so than for smartphones. Think about sensors deployed in fields, on infrastructure, in remote locations. They often need to run unattended for years on a tiny battery.
5, 10 years, you mentioned earlier.
Yeah, sometimes even longer. That requirement dictates everything. It means selecting ultra-low power MCUs that are specifically designed to spend 99.9% of their time in a deep sleep state, consuming virtually nothing. They wake up maybe for a second, take a reading, transmit a tiny bit of data, and go straight back to sleep. Without that extreme power management, large-scale IoT just isn't feasible.
Incredible. That longevity is amazing. And how do these super low power devices, often miles from anywhere, actually talk back? What kind of wireless tech makes that possible without killing the battery?
Right. Standard stuff like Wi-Fi is usually way too power hungry for these long deployment scenarios, and Bluetooth is too short range.
Hmm.
So the IoT world relies heavily on LPN technologies, low power wide area networks.
LPN. Okay, what are some examples?
Common ones you'll hear about are LoRaWAN and NB-IoT, narrowband IoT. These are specifically designed to send small amounts of data over very long distances, kilometers, potentially using minimal power. They trade off data rate for range and power efficiency. Perfect for that sensor in a field sending just a temperature reading once an hour. It's all about finding the right balance for this specific application.
Fascinating. A whole ecosystem of specialized communication for these tiny, long-lived devices. Okay, let's try to wrap this all up. If you had to summarize the key technologies and the core architectural ideas that define computing beyond the desktop today, what would they be?
I'd say it's defined by computing becoming pervasive, deeply integrated, and relentlessly focused on power efficiency. The cornerstone architecture is the system on a chip. So putting the whole computer on one piece of silicon, that's what untethered computing from the desk.
The arcology model.
Exactly. The dominant language for these power-constrained devices became the ARM architecture, enabling our powerful yet efficient smartphones and tablets. Then, this extends into the hidden world of embedded systems powered by simpler microcontrollers, MCUs, which act as the dedicated brains in countless devices around us. And finally, connecting these low-cost, low-power embedded devices using specialized communication forms the foundation of the Internet of Things, weaving computation into the fabric of our environment.
So it's really a story of integration, efficiency, and specialization, moving computing off the desk and out into the world in countless different forms.
That sums it up perfectly. The future isn't just faster chips, it's smarter, smaller, more efficient chips integrated everywhere.
What an incredible journey we've had today, really diving deep into this world beyond the desktop. We've unpacked that clever system on a chip concept, seen why ARM rules the mobile space, looked inside our phones, and peered into the almost invisible world of microcontrollers and the IoT. I think the big takeaway is that efficiency, integration, specialized design, these aren't niche anymore. They are the cutting edge, making tech blend seamlessly into our lives.
Absolutely. And understanding these architectures, even at a high level, is becoming really crucial. Whether you're developing software, designing hardware, or just want to understand the tech shaping your world, knowing about SOCLIs, ARM, MCUs, it's fundamental now. That shift to integrated power-efficient design is everywhere.
Well, this has certainly laid some critical groundwork, and it sets us up perfectly for what's coming next. We hope you'll join us for our upcoming series, The Future of Computing Hardware, Breaking Barriers, where we'll explore even more mind-bending developments. Thank you so much for joining us for this deep dive today. If you found this valuable, please do subscribe to our channel, Tech AI and beyond, so you don't miss out on future explorations. Until next time.